Good day, viewers and fellow math enthusiasts. Today, we're diving into the fascinating world of polar coordinates, a powerful and visually intuitive way to represent curves that would otherwise seem complex in Cartesian form. Our focus: learn how to graph polar equation involving circles and getting introduced to limacons. We'll break down step-by-step solutions, explore key patterns, and walk you through examples so you can master this essential skill in trigonometry and pre-calculus. Let's begin with the basics: how to graph circles in polar form. Let's start with the polar equation. R equals A times cosine theta. This equation describes a circle, but not just any circle. In this form, the variable r represents the distance from the pole, or origin. The angle theta determines the direction of the point from the pole. The coefficient a tells us about the size and position of the circle. Now, depending on whether a is positive or negative, the circle will be positioned differently. Here's what we do. Identify the value of a. In this case, a equals 4. Because it's cosine, the circle is aligned along the horizontal, or x-axis. Since 4 is positive, the circle lies on the right side of the origin. The diameter of the circle is equal to a equals 4. The radius then is 4 divided by 2, which is 2. The center of the circle is 2 units to the right of the pole. From this graph, begins at the pole 0 and 0 extends to 4 units along the x-axis. The center is at 2 and then 0, and the top and bottom points of the circle are 2 units above and below the center, forming a perfect circle centered at 2, 0. You simply I mean 2, 0. You simply draw the circle using the center and radius. That's the complete graph for r equals 4 times cos theta. What if a is negative? R equals negative 6 times cosine theta. Let's try another one, this time with a negative coefficient. A equals negative 6 because of the cosine theta. The graph is still horizontally aligned, but now, since the coefficient is negative, the circle lies on the left side of the pole. The diameter is still 6 and the radius is 3. The center of the circle is now 3 units to the left of the origin at negative 3 and 0, 0. The farthest point from the origin is 6 units left at negative 6 and then positive 0. To graph this, the circle starts at the pole again, extends leftward, has a center at negative 3, 0, and a radius of 3. The equation r equals negative 6 times cosine theta therefore gives a circle mirrored across the origin from the first example. Now, let's shift from cosine to sine. For the equation r equals a times sine theta, the behavior is similar, but instead of a horizontal alignment, we get a vertical one. Let's try 2 examples, one positive and one negative. In this example, a equals 2 to diameter, which is 2. Radius equals 1. Since this is a positive sine function, the circle will be positioned above the x-axis. It's aligned along the y-axis now. Now, let's look at the same sine function but with a negative value. A equals negative 8 and the diameter of it is positive 8. Radius equals 4. Since the value is negative, the circle will be below the x-axis. Center is at 0 and negative 4. The graph starts from the pole and curves downward. The bottommost point of the circle is at 0 and -8. The center is 4 units below the pole. So r equals -8 times sine theta produces a downward facing circle centered beneath the origin. Next, up in our polar journey, the fascinating Lemacon curve. The general form of a lemacon is r equals a plus minus b times cosine theta, or r equals a plus minus b times sine theta. These graphs can take many shapes: dimpled lemacons, lemacons with inner loops, convex lemacons, and perfect cardioids. The key to knowing the shape of is the ratio of a divided by b. Let's start with this form. R equals 3 minus 4 times sine theta. What kind of graph is this? A equals 3 and b equals 4. So a over b equals 3 over 4, which is less than 1. That means we're dealing with a lemacon with an inner loop. To sketch it, it opens downward since we are using negative sine theta. The graph forms a petal-like shape looping inward through the pole. It reaches a minimum value of at theta equals pi over 2 and maximum at theta equals 3 pi over 2. Visualizing this involves plotting key points for theta values like 0, pi over 2, pi, 3 pi over 2, and 2 pi, then smoothly connecting them. The inner loop arises because at some values of theta, the function r becomes negative, and meaning the point is plotted on the opposite direction. So far, we've covered how to graph polar circles using r equals a times cosine theta and r equals a times sine theta. And then the second one is the impact of positive versus negative coefficients. The third one is how to find radius, center, and direction. And lastly, we began exploring lemacons where the form r equals a plus minus b times sine theta or cosine theta brings in complex and beautiful curves. Whether you're a student tackling pre-calculus or an enthusiast sketching polar roses and cardioids, understanding these foundations is key. And remember, math is not just numbers, it's geometry in motion, especially in polar coordinates. This is Noraini Bihajula reporting from the world of mathematics, where every angle tells a story and every curve has character. Stay curious, keep plotting, and may all your functions be smooth.